Welcome to episode 12 of the Physiology 225 podcast. I'm your host, Dr. Jim Davis, and today we'll explore the fascinating process of action potential conduction, how these electrical signals travel down the axon to communicate with neurons or other effector cells. In our next episode, we'll discuss refractory periods, but for now, let's dive into how action potentials propagate along neurons. So what do we mean by action potential conduction? Well, this is the process by which the electrical signal of an action potential is transmitted along the length of the axon. This is essential for communication between neurons and other cells in the body. The conduction of an action potential depends on multiple factors, such as voltage-gated ion channels opening and closing, local currents created by the movement of ions such as sodium, and the structure of the axon, including its diameter and whether or not it's myelinated. So let's start off by talking about unmyelinated neurons. In these neurons, action potentials are propagated along the axon in a continuous manner. Here's how it works. The first segment will be depolarized, and when this segment is depolarized, voltage-gated sodium channels open, allowing sodium ions to rush in. This influx of sodium creates local currents that depolarize adjacent sections of the axon membrane. Voltage-gated channels in that next section open, continuing the action potential. What's also important to know is that voltage-gated potassium channels also open, allowing potassium to exit the cell and restore the resting potential in the previous section. This sequential process repeats until the action potential reaches the axon terminal. While effective, this type of conduction is slow, much slower compared to myelinated neurons. So we have myelinated neurons and the process of saltatory conduction. In myelinated neurons, conduction is much faster thanks to this process of saltatory conduction, which allows the action potential to quote-unquote leap between the nodes of Ranvier. Here's how it works. Myelin is an insulator, and it's something that is produced by Schwann cells, or oligodendrocytes, that insulate the axon and prevent ion leakage. In between the myelin, we have nodes of Ranvier, and these are gaps that contain very high concentrations of voltage-gated sodium and potassium channels. So the nodes are the things that become depolarized. This is the only location where an action potential occurs because sodium channels will open, and then that allows sodium to rush in. This leads to a leaping type of signal. Local currents quickly travel beneath the myelin sheet to the next node where the process repeats itself. Now, saltatory conduction is significantly faster than continuous conduction because the action potential doesn't need to occur at every segment of the axon. Additionally, sodium influx is much greater in a myelinated neuron due to the high concentration of those voltage-gated sodium channels. There are other factors that affect conduction velocity as well. These include axon diameter. Large diameter axons have less resistance to ion flow, which allows the signal to propagate faster. Think of this in terms of a freeway. It's a lot easier for traffic to get backed up on a 2-lane highway as opposed to a freeway that might have 6 or 7 lanes in each direction. Myelination also conducts signals much faster, as we just talked about, and this is again due to saltatory conduction. Finally, we have temperature. High temperature increases the speed of ion movement, and if ions are moving more quickly, then the action potential will move more quickly down the axon. So I want to point out some key differences between myelinated and unmyelinated axons. Myelinated axons are much faster because they can undergo saltatory conduction. Myelinated axons use less energy because ion exchange is limited to the nodes of Ranvier, as opposed to unmyelinated neurons that have exchange occur all along the axon. Additionally, myelination ensures that signals arrive quickly and reliably, which is essential for coordinated movements and rapid responses. Just to give you an idea of the speed and the efficiency, myelinated neurons can have an action potential travel at about 100 meters per second, whereas unmyelinated neurons, that speed might only be about 1 meter per second. So let's summarize with our key takeaways. Action potential conduction is how electrical signals travel along axons. In unmyelinated neurons, conduction is continuous and slower, with action potentials occurring sequentially along each piece of the axon. In unmyelinated neurons, saltatory conduction allows the signal to leap between nodes of Ranvier, significantly increasing speed and efficiency. Factors like axon diameter, myelination, and temperature affect conduction velocity. And so with that, we are done for episode 12. I hope this episode has illuminated the fascinating process of action potential conduction. Join me next time for episode 13, where we'll delve into refractory periods and their role in neuronal signaling. Until then, keep questioning, keep exploring, and stay curious.